vehicles and modernizing development environments to support the increased speed that we need. And also, today, in my presentation, I want to focus on one very important aspect, which is OTA, but enabling OTA in a way that avoids risking your reputation, right? So, because safety and security, cybersecurity issues can be devastating. We know, you have heard probably about UNR 155 or the other name UNECE Work Condition 29, which is a new regulation implemented by many countries, and it demands automotive OEMs to implement a cybersecurity management system, and that means they have to monitor their software inventory, and they have to also monitor what's going on with the vehicles in the field and provide updates. And if you read surveys or you talk to colleagues here at this conference, you might find out that this is a challenge for maybe everyone. Implementing this in an efficient way and also in a safe and secure way is really a challenge. So let's first try to understand what is the meaning of OTA for the software-defined vehicle. And the analogy to this is what would be the value of a smartphone if it didn't have an app store. It would probably be close to zero, and the same will be true for software-defined vehicles. So we need OTA for fixing cybersecurity issues. We need OTA to provide new applications and updates of the platform software. And the related safety issues, challenges around OTA are maintaining reliability, which is not directly a safety issue, but reliability in the sense that if something goes wrong, there is no expert available, unlike in earlier times, right? This is the main challenge. It has to be really reliable, and it only is allowed to start the update when the vehicle is in a safe state. So the vehicle has to be really taken care of. And cybersecurity, well, here we have the classical challenges, I would say. We have a new attack surface provided by OTA, but OTA is also a vehicle to fix cybersecurity issues. So it's both a solution, but also a new risk. And so we need a crypto architecture, we need integrity and confidentiality of update images. Let's go with an example here. We have in the presentation this morning, we have talked about BMS already. So let's take a battery management system as an example here as well. We have an EV, a fast charging station, and it's parked. The BMS is, of course, safety critical. For example, it monitors it keeps the battery temperature in range. What do we do if an update is available for the BMS at this point in time? Do we just, what are the conditions that we need to check? But also, what are the cybersecurity implications? So could it be that there is a tampered OTA update image and someone tries to steal our car with that by just bringing it into a safe state, which is but also an insecure state, right? So there are a lot of things that can go wrong. So let us to recap a bit, just have an analogy again for safety and security. Safety is about protecting the human from the system, and you can say that security is protecting the system from the human, right? So we have a fuse, which obviously protects the human from an electric shock, or we have a gate and a fence which protects a building or a system from someone malicious to enter this protected area. And this analogy is now important as well for this comparison here of our cybersecurity and safety norms. We want to basically show ISO 26262, which is the functional safety norm, and ISO 21434 for cybersecurity. They have a lot of things in common actually. So, for example, they are risk-based. So they all are based around identifying as many as risks as possible and assessing basically a risk level, and then to decide what to do with this risk. They don't define the development process, but it's a precondition. But they do define organizational things like roles and responsibilities of roles, cybersecurity manager, functional safety manager, and so on. They recommend techniques to find issues like inspections, code inspections, for example. And they, depending on, for example, the safety levels, they recommend different techniques. And they both at least briefly recognize that there is a mutual influence. So there is one phrase in each of these norms which says, yes, you have to take the other factor, cybersecurity in the case of safety and vice versa, into account. And the differences then is basically around the focus in the development of the system. In functional safety, you focus more on the development phase. At the end of the development phase, before SOP, you do a safety case, and then you consider the system as finished, developed, right? In cybersecurity, it's recognized that even if you do a lot of risk management during the development phase, things can still happen in the field because the system, as soon as it goes on the road, will already have new vulnerabilities. So you have to continuously manage that. And that's why in functional safety we talk about fault management, handling faults, avoiding faults as much as possible, and in cybersecurity we talk about vulnerability management. And that means when we look at the change frequency, we can see that functional safety in the operational phase, so after SOP when the vehicle is in the field, is basically focused around observing and reaction. So the ISO 26262 says you have to have some field monitoring in place. You observe if there is a safety incident happening in the field, and if something happens, you have to react. But it doesn't say that you have to proactively do it. Right? So it's something reactive. If something happens, you should probably better do something about it. In cybersecurity, I would say it's more like in the direction proactive, fix issues before they materialize, and that requires, and this is what the challenge is, this is why we have this requirement to have a safety, cybersecurity management system. And this is the challenge. Okay, so we know the challenge, we want to know how to solve it, right? I want to focus on three main things. First is the automotive OS, the second is safety and security as second and third, safety and security aspects in the EE architecture. The automotive OS is also a frequently used term, and it basically means the main feature it provides is an abstraction between the application layer and the software platform. And the idea is to have a stable API for stable APIs for applications so that they can be reused across different models and years and across vehicle generations. Right? So this is one of the main ideas of the automotive OS. And regarding safety and security, they provide, let's say, the one key thing is that they support highly integrated zonal and central ECUs. Right? We have seen a lot of diagrams in this conference already, how this looks like. It provides safety and security system properties, so you don't need to fix those issues or keep track of these issues on application level. And the software platform must ensure proper integration, update, and separation of components. Right? So this is a key function. And now let's switch to the EE architecture. This is a slightly different presentation of EE architecture. You basically, it's separated between, in the middle, you have this HPCs, right? You have 2 to 3, depends on which OEM, basically. Here on this level, this is really the focus area of the SDV. This is the differentiated part where OEMs want to have ownership, and which is very dynamic. The right-hand side of the slide is the zonal and the sensor actuator ECUs. They are the ECUs that we already know today, and some of this might become a commodity, so maybe standardized so that OEMs just buy this as a product, right? Not individually developed for each OEM. And if you look at the change frequency, it's clear that the SDV focus area will be much more frequently updated than the other one. Will it not be updated at all? No, I would not go so far as well, because we have seen that our customers also want to have firmware over-the-air capabilities for classic AutoSAR ECUs. So we know that this is also of interest to provide updates on the zonal and sensor actuator ECUs as well. And regarding a safety architecture for OTA, what do we need to prevent harm, right, hazards? So basically, you always have an update package. So you receive an update package from the backend, and you have a UDS client to distribute packages to the classic ECUs. But before, and then of course, you need also to be able to update these more modern HPCs. So you would probably also have an update slave on this ECUs, which doesn't use UDS, which uses some new protocol to do this. And then the thing is, we need to coordinate if it's now okay to start an update. And we do this basically by implementing the vehicle state master in some place in the ECU. So this is really functional safety critical. And the update master needs to ask, okay, can I now start the update? And now the update vehicle state master basically assembles the state from all other ECUs in the car using local state handlers, a global state which says, okay, now I'm ready to receive an update, to start an update. The user has probably given the consent to do it. The battery is in an okay state, the vehicle is parked, and so on. So this is a potential, this is the basic thing you need for handling functional safety or preventing functional safety hazards. And now let's compare this to what we would need to cope with or to handle cybersecurity issues. And cybersecurity actually, one other thing before that. I talked about firmware over the air updates briefly. And classical ECU update works like shown here, right? So you have somewhere an update in a tester. You want to connect to the ECU. You delete the old image. You download the new image, and you reboot the ECU, and you have the new version there. This takes a while, and if something goes wrong in between, you have to start over again. So the downtime of this ECU is rather long. On the other hand, to speed this up, basically, you can add an external flash to the ECU. So you basically copy the new image first to this external flash, and then during the installation phase, you only copy it from the external to the internal flash, which is a lot faster than copying it from UPS. And by this, you can now accelerate or shorten the downtime of this particular ECU, right? So you can do things in the background, but you still have a significant downtime. And what we see increasingly now, and especially for zone ECUs, is something like this. You have a dual bank approach, which you already know probably from HPCs or from smartphones. Right, so you have in the internal flash, you have an A and a B bank for the fallback, and this allows you to have what we call reproc module, a background updater, which basically downloads the image to the inactive bank, and then just resets the ECU, and you have the new image, and everything else happens in the background. And this is quite convenient for firmware over-the-air update use cases to do things more in the background and to reduce the downtime. Right? This can also improve reliability. However, on the downside, it increases the hardware cost as well. Right? So hardware costs, we need more internal flash. It could be significant. And now let's go to the cybersecurity aspects of it really quickly. And here it looks quite different, right? So in the functional safety, it's more collaborative, and they trust each other, and they ask what is the vehicle state. And basically in cybersecurity, it's more like different security zones which have to be strictly separated and which don't trust each other. And typically you would have zone 1, which is the external interfaces to the vehicle. Then you have the layer 2, which is basically an HPC or multiple HPCs, this SDV area, and layer 3, which are the individual ECUs. And all of them are basically paranoid. They don't trust each other, and so that means when the TCU makes a connection to the backend, it creates a secure connection. It needs to check the authenticity of the backend, of course. Right? The update master as well checks the update integrity of the image. It checks the authorization of the backend again, maybe. Right? So, and this is basically the bit of a contradiction. And for functional safety, there's a collaboration, but for cybersecurity, we need to be really strict and check everything that comes in from another layer. And this is why also, for example, the secure bootloader in the ECU, maybe it's a modern firmware over-the-air background updated, but it could also be a classic bootloader. This one also wants to check the integrity of the new image. It also wants to have an authorization to use a UDS 29, and it of course does a secure boot. So we need a multi-layer cybersecurity defense. That's the bottom line. So let's come back to the initial example. Update is available. So we now know that at the very minimum at least, we could continue charging under VMS supervision, and then we could basically briefly interrupt the charging process and then ask the vehicle state manager whether now we can actually start the update and have a decision based on the global vehicle state. And for cybersecurity, we need to do all the cybersecurity checks, for example, like checking the update integrity, the authentication, and the authorization of the connections. Okay.